Okay. So, good afternoon. We're Team LunAR-X working to reshape the moon. Let me introduce the team members. We have Vibhakar, Vivek, Hariharan, Anish, and I'm Dhruv. So this project was made possible due to the constant guidance and support of our wonderful sponsors, Red and Caterpillar. Humanity has come a long way since the first moon landings, and space is not just about exploration anymore. It is time to start building things. There are many people all around the world that are working full steam ahead, trying to ensure the future of our species in space. We will require extensive infrastructure out there on the moon, on Mars, etc. But there's a catch. It is extremely dangerous for humans to be out there building things, especially in those hefty spacesuits. But it's a perfect opportunity for robots to shine. So how will this endeavor look like? After a 3-day journey and a few critical moments of landing, by the time our rover reaches the moon, the operators back home will already have a task ready for it. What will the task be? To ultimately build complex structures like habitats and landing pads, we need to start with the fundamental shape of construction. That is the berm. The berm is used in construction to build barriers and outline layouts. And what will we use to build this berm? Lunar regolith, the sandy, coarse material which is found all over the moon's surface. And we're going to require huge amounts of regolith to realize our endeavor. That is where our rover comes into the picture. The Lunar Autonomous Regolith Excavator, or LunAR-X for short, built for this exact purpose. Now, what does it need to start building this berm? The first thing it needs to answer is what to build. So the operator needs to specify the length and the height of the berm that we have to build. For today's demonstration, since we want to show the capacity of the system, we're going to give it minimum dimensions, that it has to build a berm that is at least 30 centimeters long and 15 centimeters high. The second thing it needs to know is where to build the berm. So for the purposes of this demonstration, we're going to be building in the smooth flattened part of the moon yard. Once it knows these two things, the rover is ready to build the berm. For today's demonstration, we'll be teleoperating the rover. Let's begin.
All right. Now that we know our missions, let's see our rover in action. First, our rover will navigate to the source region and excavate. One of the significant challenges of lunar excavation is a low gravity environment on the moon. The traditional excavation tools used on Earth, like bulldozers with these bucket mechanisms, fail to work on the moon. The low gravity makes it challenging to apply downward force and excavate material. This is where the razor mechanism comes into place. Developed by NASA, the razor tool has counter-rotating drums with protruding teeth and is specifically designed to excavate and transport lunar regolith. Inspired by the razor platform, we developed our own excavator. We make use of continuous rotation, and it has 4 cutting edges. It's made out of aluminum and steel, and to monitor the amount of regolith filled, we have designed it in such a way that we have 2 transparent faces on each of the sides of the drum. As the tool rotates, it excavates material, achieving a maximum fill capacity of 50%, which it does in just 12 rotations. Once the tool reaches maximum capacity, the regolith inside the drum can be deposited by rotating the drum in the opposite direction. As the regolith settles down, it assumes a berm-like structure. Imagine a conical shape extended along one side. At the end of the deposition process, we have a berm ready. But how do we know how well we have done? Let's evaluate our berm.
The height is about 9 centimeters and the length is about 40 centimeters.
Now let's look at how we do it. Our rover has an inbuilt berm evaluation system that it uses to autonomously estimate the height and length of the berm. The perception system scans the construction site and finds the biggest mound of regolith. The length of the berm is estimated by fitting a best fit line through the berm. The volume is calculated and is compared against the target volume to estimate the berm progress. Moreover, the rover has a 3D stereo camera, which can be seen here. As the rover moves towards the berm, it sees an elevated terrain, which is an accurate representation of the berm. Now let's talk about the productivity of the system. Our rover is capable of excavating 9 kgs or 19 pounds of regolith per cycle, which lasts for about 3 minutes. Given abundant energy, our rover is capable of excavating more than 2 tons of regolith per day. As we complete the second excavation and dumping cycle, we see that the berm enlarges in length and height, and we will soon evaluate the berm again to measure its progress. This is a top-down view of the first-hand view that the rover sees. The region mentioned in black signify the berm, and the rest of the region signify the ground plane. Let's evaluate the berm for a second time.
So height is about 14 centimeters, the length is about 15 centimeters.
The system is being teleoperated right now, but moving forward in the future, we will make the system better by incorporating autonomy. By providing the necessary inputs, we can enable the robot to perform all the operations, including excavation, navigation, and deposition, all autonomously. However, before we can achieve full autonomy, there are a few critical components to be addressed. Firstly, we need to ensure that the robot knows where it is located. But the construction sites on the moon are huge. While on Earth, we rely on GPS to track our position, but on moon, we don't have such a system. Therefore, we use the total station infrastructure, which you can see is located at that corner. The total station shoots lasers to track the reflective prism that is mounted on the robot to track its position. Additionally, we also have wheel encoders on the mobile base and IMU to calculate where the robot is heading at. To validate the accuracy of the robot localization, we will be performing a loop closure maneuver after the dumping procedure.
We are starting to close the test.
In the display, we can see that the loop has been completed successfully, and we can validate that the localization tracks the rover with such good precision. Now, moving on to the next phase of the autonomy, we have the mapping. The robot should be able to see what it's looking at and what it's building. So for that, we have cameras in place that builds the map that shows the height of each point in the terrain, and it acts as the guide for the robot to check if it's building the berm that is as per the desired configuration. Now that a robot has information about its position and the environment it's operating in, the robot needs to plan its operations for autonomous operations. We envision a complex construction site that has multiple excavation and deposition zones. In that, a robot should be capable of planning its operations, minimizing the time required to build the berm, optimizing all the tasks such as excavation, navigation, and deposition. Another crucial aspect of autonomy is material volume estimation. The robot must be able to estimate how much material it has excavated to plan its operations further. The motor current required to rotate and the actuator current required to push the excavator upwards depends largely on the weight of the material inside the bucket drum. So we will use this to model our algorithms to estimate the weight, and hence we can even estimate the volume using the density. As a validation for the berm evaluation model, we will now be measuring the berm manually and checking with the data we have generated.
The height is around 16 centimeters, which is the mandatory requirement for certificate.
In conclusion, we have built a production level machine with an innovative tool, excavation tool design that is compatible with the lunar terrain. As promised, we have successfully built a berm that meets the mandatory desired berm configurations. We also validated the accuracy of the localization system and also have demonstrated the berm evaluation module. As we move forward, we will be improving our system by incorporating both planning and mapping stack and utilizing every opportunity to improve the system. Once again, thank you again for attending our demo, and we would like to extend our special thanks to Red, Eric from Caterpillar, our senior team Cradle Grader, and Chuck, Tim, and Abhishek from Field Robotics Center. We are now to open any questions that you may have.
Thank you. So it was currently it was just visual to see there's like less than 15 centimeters error of it. So that was our system requirements. Yeah.
For the localization, we are using the total station encoders and the IMU, and the accuracy that we're currently getting is around 250 centimeters.
So the most fundamental thing we can bring, we can build using this is a barrier for landing pads. So when a rocket will land on the moon, it will kick up a lot of lunar dust. So lunar dust is already known in the space community to be pretty invasive. It gets everywhere in the suits. So when the rocket will land, it will kick up a lot of dust and it could harm the habitat and other astronauts that might be close by. So the initial structure that we would want to build is a full barrier around the landing site so that none of the plume from the rocket landing or the dust affects the habitats and our astronauts. That is the stretch goal. If we're trying, like, how big of a circle can you make?
And the proof of collectively, the data is an actual required accurate, but the final factor is an actually so this data is that getting like from current sensors or
cycles of excavation. So like the drum rotation, that actually depends on the speed of the drum rotation as well. So we were doing it slowly for the audience to observe right now, but the full capability that can fill the drum in 12 seconds.
what was the feedback like? Did you control it manually or?
So yeah, so right now we're teleoperating it. Next goal for the next sem is that we are going to use the drum motor current to estimate the amount of sand inside.
And the same for the dumping cycle as well.
Yeah. So after we dump, we have to figure out that did we dump all the material or not. That's how we'll use the current to estimate. Well, and it was me. Yeah.
And
so right now I was using it with line of sight. The terminal just displays the status and diagnostics of the system. Yeah.
The storage station is very accurate to estimate the display. So, like we can't just use the storage station because it doesn't give very continuous data. So when we use it with the wheel and rollers, the localizing output is new, but it can arrest for the reset that we get from the computer.
And we use this because this is the technology which can actually be used out in space. So it's like this. Yeah.
Is there any limitation on that?
It's just the battery.
Okay.
We can like emergency stuff. So we have two systems. So right now it is actually lock with the software. So even if I go anything, that's what I'm doing. Hardware is I don't know what I will do. Actually, hardware is on it. So now I can do whatever it's been done. So even if I remove the software, you can see the red line is going on with it. Yeah, so the status indication lights on the top panel are the first one is power, where the computer power or not. The second one that is being is the heartbeat, which tells us that the system is light and has a crash. Two white ones are on the operator mode and the task mode, it is behaving both by using the autonomy. And the last one is for the software on the current. Yeah, we didn't have two cameras, but the recently reported was that we don't see any of the GPU of the computer. And pictures with this one camera. The reason we initially kept the two cameras was we wanted the light field of view as much data as we can get, but the camera can be good. So there is this molecule is So for the scope of this project, we didn't want to put a time restriction because we already had a lot of restrictions building on the campus. We will explore time requirements. Although we're fairly certain we won't be on that much of a time crunch when it's just robots working on it. Yeah. So that's why we're exploring if you want to build a circle, we have to do it pretty fast because it would require multiple excavation cycles within the 20-minute time span. So we are exploring that. So we might not shoot in explicit time limit terms, but with the scale of the things that we're building.
So the planner we build will be optimized for the time of the build.
Yeah. Excellent.
Seems to be very good time.
Yeah.
Forward, 70 back, 90 apart. Because excavating volume reversal for larger number of forward runs that are variations on normal approach.
Yeah. So that is what the planner will be optimizing for. So for the demonstration, we wanted to keep the excavation closer to the audience so they could see the drum filling. Later on, the autonomy part, what we're going to implement is that it will keep excavating as it moves towards where it has to turn. So it will optimize for the time as it comes. We can.
In this area, yes.
One because 1 minute it takes for the drum to fit. Yeah, 2 minutes is
there any reason why it gets slower?
So when the drum is rotating very fast, so after a point where it has filled up to 50%, it spills out most of the material it has excavated. So we can even we can even try to optimize the rotation speed according to the fill capacity so that it doesn't spill out, but it can fill the material as fast as it can.
Time always matters.
Like any other questions, or if someone wants to stay and operate the rover, feel free to after the presentation. Happy to, but yeah, that's our presentation. We are open for any other questions. Thank you.
Everybody goes. You didn't make us to add a lollipop.